Okay, so another example. Right, so here we have as our surface the sphere center at the origin, radius 3, oriented outward. So again, now just a reminder, if you're talking about flux, talking about a scalar surface, vector surface integral, the domain cannot just be a surface. It has to be an oriented surface. You have to indicate what orientation. Otherwise, there's this ambiguity of which way are you talking about? Which way is the correct which way is the positive direction through the surface? So yeah, we got a domain and we've got a vector field. Now, there is a temptation to look at what we see here and say, okay, I've got everything I need, and take a deep breath and just start plowing, right? Plug and chug. And very often, you got to do that. This wouldn't be horrifying to do that way. Notice that we can parameterize this sphere without too much trouble. We'd use the spherical graph parameterization. Just plug in rho equals 3, right? And then the spherical coordinate formulas give you a parameterization of that sphere. So, pretty doable. But there is going to be a bunch of trig. X, Y, and Z are all going to be full of trig, which means that this vector field is going to be pretty full of trig, right? Not clear we want to do that. Sometimes you get lucky and the unit normal vector is extremely convenient. So this is one of those circumstances as it turns out. Now, first of all, let's talk about how to write down the unit normal vector. Keep in mind this is a sphere of radius 3, which means that this position vector x has a magnitude equal to 3. Right, so that distance, that magnitude is 3. What can I say about this unit normal vector here? This unit normal vector, well, and I appeal just to the picture, that unit normal vector is pointing in the same direction as the position vector. Spheres are great. Right? Spheres are just chock full of symmetries. So n is parallel to x. X has magnitude 3. N has magnitude, of course, 1 because it's a unit vector. So there's really only one possible formula then. N has to be x divided by 3. And you see this on the previous page up here. N is x over 3. So we can write down a real convenient formula for that normal vector. So notice we have n, handy little formula. We have f, handy formula, and n, f dot n that you see right here. There's my f and there's my n, right? In this unit vector formulation of the flux integral, you can just compute that dot product. And it's 0, which is sort of an immediate, observation that this dot product is 0, and therefore we're doing a double integral of 0, and that adds up to 0. Okay, so like I say, sometimes you get lucky. What's the tip-off that this is going to happen? I don't know how to make a perfect answer to that question for you. One, you might say tip-off is that our surface had some wonderful symmetries, and I didn't really need to use fancy parameterizations to find that normal vector. It was easy. So, maybe write it down real quick. Just who knows? It might be convenient, might be useful. Okay. All right. Okay, so there is an oddly powerful set of analogies between vector line integrals and vector surface integrals, and I think this is worth pointing out for a combination of reasons. I'll say a couple words about why ultimately it happens. But first of all, let me talk about how surprising it's going to be that there will be analogies. Let's think about where vector line integrals came from. Vector line integrals came from considering work, where we were thinking about the vector field as representing force. Right? So vector line integrals came out of thinking about forces and work. Okay, let's set that aside. Where did vector surface integrals come from? They came from thinking about flux, where the vector field represents a fluid flow. So fluids and fluxes motivated surface integrals for us. Forces and works motivated line integrals for us. These physical applications are completely disconnected. Right? There's no clear connection between those two applications. So, and yet there's going to be a strong analogy between these two kinds of integrals, and we've already seen some of these analogies as we've been moving along. So I'm going to try to underscore what those analogies are, and then I'll say a couple of words as to why this happens. It's not a coincidence. It's going to look like a coincidence. Okay, so we'll start with the picture I have drawn here. I have a picture of a parametrized curve on the left. I have a picture of a parametrized surface on the right. Apologies for the fact that these parameterizations are drawn downward. The page is only so wide, right? And needed to have one on the left and one on the right, so they had to be up and down. So anyway, it looks a little strange, but this is just a parameterization of the curve. T-axis, image curve. UV plane, image surface. Okay. All right. So now let me point to some specific objects of interest. We know that the velocity vector plays a role in the calculations on a curve, and the dt scalar over here. Let's see here, and then we have the unit tangent vector plays a role, as does also this ds scalar. And then we it all kind of comes together with this dx vector. Y'all recall that I'm a big fan of the dx vector. There is that little picture. Okay, now let me talk about the analogous objects, and I'll talk about what the analogies are once I get them all highlighted. The analogous objects over here in this parameterization, we have our capital N vector. We have our du dv area. We have the unit normal vector. We have the ds area scalar there. And then it all kind of comes together in this ds vector. And the way I have things color-coded here is suggestive of the analogy that I want to talk about. So let me go down to where I can... Oh, is this all going to fit? Oh, did I? Oh, it's just a little too far down here. Okay, no sweat. Let's talk about ds versus dx, both in purple. dx and ds. Okay. I'm going to try to keep my color coding consistent. dx is x prime dt. ds is capital N du dv. X prime and capital N, both colored yellow up here. dt, du dv, both being orange up here. So here's the analogy. The dx vector and the ds vector, both of them are vectors computed with derivatives from the parameterization times sizes in the pullback domain. Right? Now that's x prime dt for curves. It's capital N du dv for surfaces. But the pattern is pretty strong. Okay? So both of these vectors, we've already talked about the analogies between the dx vector and the ds vector. Both of them are computed from derivatives times differentials. Pullback differentials. Okay, alternatively, oh gosh, color choices, right. Dx is t times ds. The ds vector is little n times ds scalar. Green vector times blue size. So again, the pattern continues, right? This dx vector is the unit vector orientation times the size differential ds. So unit vector orientation times size differential. Likewise over here, the ds vector, unit vector orientation times size differential. Same pattern. I mean, it's weird. Right? Everybody see what I'm talking about? It's very strong analogies here. So these continue. You can look at the formulas for how we write down different kinds of integrals. While I'm here, let me observe that continuing the analogy between n and x prime is the vector whose magnitude is the stretching factor in the curve context. N is the vector whose magnitude is the stretching factor in the surface context. So that's kind of neat. Okay. Look at all the different ways we have to write these different kinds of integrals. We can write each of them in terms of the vector differential. Again, these tend to be my sort of generally, all else being equal, kind of preferred notations. Both of these can be written in terms of parameterizations, pullbacks. Both of these can be written in terms of unit vectors and scalar sizes. So, a lot of strong analogies. So now, how could this be? This calculation over here is about work and forces. This calculation over here is about fluid flows and fluxes. Completely unrelated calculations. The layout of the calculations, though, the analogies is very strong. So what's going on there? This is where I have to start getting kind of ambiguous. I can't tell you the whole story here, but it turns out that both of these constructions that we've just come up with are special cases of a more sophisticated and powerful construction called integrals of differential forms. And it's just way too much for Math 212. We couldn't possibly talk about it here. So that's good news, right? You're not responsible for integrals of differential forms. But it does kind of, the mere fact that there are these things called differential forms and that they're integrals, in special context. If you talk about the integral of the right kind of differential form over the right kind of domain, it simplifies down to a vector line integral. And a different kind of differential form over a different kind of a domain simplifies down to a vector surface integral. So the point is, these two calculations, it's not that we used one kind of integral for one and one kind of an integral for the other. It's that both of these applications can be addressed by integrals of differential forms. And integrals of differential forms, just, the details are a little different in each case. But, well, of course there's an analogy between them. They are the same thing. Both of these are integrals of differential forms. Okay. So, anyway, that's just a cultural point. I am going to talk more about that unifying, mysterious unifying underlying factor that, when we get into Chapter 6, there's some other really nice manifestations of this. But we're not going to say anything precise about any of it. Okay, let's see here. Last thing real quick, let's talk about flux through a curve. This is just a sort of a dimensional alternative. We have up to now been talking about surfaces in 3 space. And a surface in 3 space, you could imagine a 3-dimensional fluid flowing and to some extent flowing through that surface. Drop it down 1 dimension and you can talk about a curve in 2 dimensions. You could talk about a fluid flowing in 2 dimensions, and you could reasonably ask how much fluid is flowing through that curve. Right? It's the same idea, 1 dimension lower. Okay. All right. So no big deal. Flux through a curve. It's the analogies are very strong. Flux through a curve says how much fluid is passing through the curve per unit time, just like with three-dimensional fluids. Just like in the three-dimensional case, only the part that's actually perpendicular to the curve actually matters. To the extent that the fluid is flowing parallel to the curve, who cares? Right? We're only interested in the fluid flowing perpendicular, and that multiplies by length to give you flux. Length instead of area. Again, dimensionally, just one dimension down. And then this formula motivates this formula for a flux integral over a curve. L is just ds on each little piece of curve, add up over the whole curve. Okay. So the question I want to address now, at having defined flux through a curve, is how do we go about computing this thing? Notice that this integral is not something that we have tools for. We don't know how to compute integral over curve dot product in ds. Right? That in is different. That's kind of new. I do know how to compute an integral of something dot t ds, because that's just a different version of our, that's work integral, basically. Vector line integral. Can't deal with the in. Okay, so the way we deal with this that we can't deal with is clever little observation here, and that is as follows. If you have a piece of curve, here's a piece of curve. Oh, let me use a different color. Here's a piece of curve like this. I'm just going to make this clever observation that if your vector field is like that, and if the normal vector is like this, and thus I need to compute this dot product, f dot in, just turn everything there 90 degrees counterclockwise. Let's see what we get. I'm going to get a different vector. I'm going to call this f perp. It's not the perpendicular component. This is just a new vector, a 90 degree turned field vector. But notice that when I turn the normal vector 90 degrees counterclockwise, I get the tangent vector. Right? And so the observation is that, well, if this is just I'm turning everything 90 degrees counterclockwise, that dot product, f dot in, is the same as that dot product, f perp dot t. I'm going to rewrite f dot in as f perp dot t. And everything kind of falls into place, as it turns out. F dot in, f perp dot t. Not hard to persuade yourself of a formula, by the way, for this f perp thing. If f has components p and q, right, then this f perp thing, it's going to have the same, just rotating 90 degrees, it's going to have the same magnitude. It's just going to have these are going to be perpendicular, therefore the dot product is 0, and we get negative q comma p. And you can just confirm that these two vectors have the same magnitude and their dot product is 0. Casual observation. So there's f perp, negative q comma p. Having rewritten f dot in as f perp dot t, notice that I find myself with t ds, which is dx, which is x prime dt. And now it's off to the races. I have a nice, crisp formula here. All right, I'm going to do a good old, plain old vector line integral. Right? Vector field dot dx. I can pull back through a parameterization as something dot x prime dt. Regular old vector line integral. All I had to do to make this work out is that I have to take the original vector field and I have to turn it 90 degrees counterclockwise. rewrite P comma Q as negative Q comma P. And now you can compute fluxes, recurves. So, clever little observation there. Thought I'd point that out. Okay. All right. So, yeah. There's another kind of integral I have to introduce here, and there's a bit of a story on this. These are called, I'm going to call these coordinate line integrals and coordinate surface integrals. We'll talk about coordinate line integrals first. And it's arguably just a matter of notation. Depends on how you look at it. But so let's dive right in. Here is some calculation. There's our line integral. Right? Dx is x prime dt, which I can rewrite like that. Now, why would I do? What's the point? This seems silly to take a nice compact, vector equals vector times scalar. We're seeing the how these are vectors. We capitalize on the compactness. So nice to write it like this. I'm expanding that out into coordinates, making it harder to write down. Not immediately clear what it is. Right? But anyway, nevertheless, this is something you can do. And furthermore, you can stretch that out a little bit, even a little bit more. Right? Stick the dt in one coordinate at a time, and you get this odd expression. But this motivates making a certain choice. Having dx written like this, let's look at that first coordinate, dx dt times dt. It practically begs to be rewritten as dx. Yeah? So what I have, and then likewise for the other coordinates. So what I have here is a motivation for a different way to think about the dx vector. I've previously thought about the dx vector in terms of how it relates to the unit tangent vector. I thought about the dx vector and how it relates to the velocity vector. Now, I've got a point of view on how to think about the dx vector in coordinates. All right. And here's sort of a picture of it. You've got your dx vector is this. And that dx vector, well, it's going to have three coordinates. There's the x coordinate of it, and there's the y coordinate of it, and there's the z coordinate of it. So, if you think about it, I mean, it's pretty plausible. This displacement, the displacement by that purple vector, well, in displacing, you're going to change the x coordinate by a certain amount. You're going to change the y coordinate by a certain amount. You're going to change the z coordinate by a certain amount. Okay. So, no big deal. Now, I am going to give you all a little bit of a pitch for a different way to think about this. And let me remind you, I've done this before, where I've taken a concept that you have a perfectly satisfactory way of thinking about it. And I've said, let's think about it instead in this weirder way. Right? And then it turns out that weirder way is how you have to think about it to extend the analogy to a multivariable setting. So that's what's going on here. I know this is going to seem strange. I want to take a different point of view on what dx scalar is. The way you're thinking of it right now probably is, well, it represents how much, when you displace, dx scalar represents how much the x coordinate changes. And there's nothing wrong with that. That's fine. Okay, here's the alternative I want to push. You got your piece of curve moving along, winding around some way, right? Let's look at this little piece of curve. Don't think about how coordinates are changing. Think about that piece of length itself, that piece of curve itself. Think about this process of how that piece of curve projects down into the x-axis. And I appeal to your geometric intuition. When that piece of curve projects down to the x-axis, there's going to be a little shadow down here. Right? And I appeal again to your sense of how stuff works. The size of this shadow is the absolute value of dx. Right now, this could go either way. I mean, it could be that the curve is going the other direction, and then when you project, right, dx would actually be negative here because, well, in fact, we are changing in the negative direction as you go along the curve right here. X is decreasing, but nevertheless, forgetting about changes, these little pieces of curve, they're shadows by projection. Now on the x-axis, the size of the projection is the absolute value of dx. Okay, now, I know it's weird. I know, why would we do this? What's the point? Why? This is much more unnatural than thinking about it as just a change in the x-coordinate. I agree. Related, by the way, which way do these pieces of curve project? The curve has an orientation on it. It's going that way. It projects, therefore, that way. If this piece of curve is projecting in the positive direction on the x-axis, consistent with the fact that dx is positive. Whereas this piece of curve, we're going that way. The projection is to the left, which is the wrong direction, the negative direction on the x-axis, consistent with dx being negative. Okay, all right, now this is just geometric observations, but again, here's the change in point of view that I want you to take. Try to think of dx now not as representing the change in the x-coordinate. Think of dx as this number whose magnitude represents the size of the shadow and whose sign represents whether the curve projected the correct direction, as in this case on the left, or the wrong direction, the backwards direction, as in this case on the right. How weird and awkward, fully granted. But that's an alternative way to think about dx. It's a weird number that has these characteristics about projections. Are we good? All right. All right, so we're going to come back to that in a little while. Here's the final sort of punchline, at least notationally, for line integrals. Remember, we just agreed that dx now has coordinates dx, dy, dz. Right, where these things are defined by these formulas. Oh, I missed the... Okay, so I've rewritten dx. Of course, our vector field has components. F has components P, Q, and R. And now here's now that we have dx written in coordinates, I actually have the option of actually cranking out this dot product. Again, weird though it might seem to do, let's go ahead and do that. Let's crank out the dot product. So that dot product then gives me I'm just writing this out as the notation seems to suggest, 3 separate integrals, p dx plus q dy plus r dz. And these are what we call coordinate line integrals. Right, this thing here, that is called an x-coordinate line integral. This is a very strange object. It's a line integral over a curve, but this isn't exactly a scalar line integral because that's dx. It's not ds. This does not represent the length of a piece of curve. This represents this weird dx thing that we just got through sort of imagining, which could be negative. Right? ds is never negative. ds is it's a length. It's a size. Right? So, and then what is this p integrand? Well, the p is just the first coordinate of the vector field. So geometrically, what does this represent? It's hard to make that case for what this represents. Nevertheless, that coordinate line integral plus this coordinate line integral plus this coordinate line integral the sum of those three things is work. Okay. All right. So why would I want to do this? Why would I want to write this like this? By the way, just for I do need to make the definitions here. Let's talk about, so going forward, what do I mean by integral of a scalar valued function times dx? What I mean by that is that just exactly as suggested by the notation previously. By dx, I mean x prime, scalar x prime dt. dy is scalar y prime dt, etc. Okay, so why would I want to do this? Who would prefer this notation to this notation? It's a tough pitch for me to make to y'all as to why you should have any interest in this notation at all. It's hard to visualize what this means. It's real easy to visualize what that means. Hey, I can see the dot product right there. Force dot displacement. This means work. We're clearly adding up a bunch of pieces of work. This is very physically natural. What the heck is this? This notation over here on the left, very compact. Right? Didn't take that many pencil strokes. Right? This thing here is like 3 times bigger. Okay, so as you might tell, I'm not a huge fan of this notation. But you will see this notation out there, so that's the first reason that you need to care about this. There are good reasons, in fact, that I'll talk about in a moment, that some people would prefer to use this notation. So you're going to see it. This is in your future. All right, so I have to show you, otherwise you won't know what this is when you see it. All right, so be prepared. My idea is that when you see this notation, and they typically come in threes like this, integral something dx plus something dy plus something dz, interpret it this other way. Take these 3 integrands and realize that they're just telling you what that vector field is, f. See what I'm saying? And that likewise these differentials, dx, dy, and dz, that's just their way of saying dot dx. So that's what I encourage. Okay, now what is the other reason? Well, and why? What are these reasons that other people prefer to use this notation? Well, this gets back to what I was saying before about differential forms. It turns out that differential forms, integrals of differential forms, look kind of like this. There are really powerful things that you can do with differential forms. I mean, they did not just make up differential forms just to be annoying. You can do crazy powerful things with differential forms. And it's too bad that we can't talk about it in this class. Really, really amazing. That's beyond this class. Again, we can't do it. But anyway, so you could make the case this is a very powerful notation. But in the context of Math 212, it's not, because we can't do that. And so in the context of Math 212, it's just clunky. Okay? So anyway, I want you to realize that this notation is out there. It's out there for good reasons. And when you see it, you should think this. Everybody on board? Okay, so let's move on now and talk about surface integrals. And it turns out that everything that we've done here, we can do an analogous thing with surface integrals. So here we go. Here is our vector surface integral, f dot ds. Let's talk about the ds vector instead of the dx vector. Well, it's in du dv. And as we did previously, let's now just write out this in coordinates. We never really have. We've just written it as xu cross xv. Very compact, very convenient. But if you want to crank this out in coordinates, okay, well, here we go. There it is. 3 coordinates cross 3 other coordinates. Write out that cross product. It's a whole thing, right? And what you end up with, as it turns out, and this is a healthy exercise, everyone should do this once in their lives, so I encourage you to do yours. The three coordinates of your capital N vector are themselves little 2x2 determinants, as it turns out. So here's just a reminder of the what these mean. So for example, this one, partial xy, partial uv, that little 2x2 determinant. All right, now that's what n is. Now don't forget what we're going to do with n. We're going to take n and we're going to multiply n times du dv. Right? So what's going to happen when I take this formula for n and multiply by du dv? Each one of these coordinates is going to get multiplied by du dv, and altogether I get that ds is all of this. And you can see in here the n that's being multiplied by, I forgot my color choice. It's being green. Okay, that's being multiplied by du dv. Okay. All right, and so here we are again. What should I call these things? When we were looking at dx vectors, and we had got to the point of, hey, what should I call these things? Derivatives, kind of fraction-looking things that involve derivatives, times differential. Derivative times differential, dx dt times dt. Oh my gosh, I really want to call that dx. So, well, what are we going to do here? What am I going to call these things? What am I going to call this? I really want to kind of cancel those. I really like to call this dx dy. But I'm a little uncomfortable with that because this notation here means change of variables stretching factor, and where is the change of variables? I mean, is there a function here? Am I actually viewing an area over here and an area over there? And is that what's really going on? Can you really do that? And it turns out that hidden in a way that we haven't thought about, it is. So I want to show you now how I really not only can but should think of this as a change of variable stretching factor being multiplied by du dv, the input area, and therefore I should think of this as the output area dx dy. And here's where that is. Let's go to the picture over here. Keep in mind, this is what a piece of surface looks like in a parameterization. Here's our piece of surface. Right, and the ds vector has magnitude equal to that area, which is ds, scalar. All right, so keep in mind further that parameterizing this piece of surface means that I'm going to view x, y, and z as functions of u and v. There is our parameterization. Now, that gives me x, y, and z as functions of u and v. That's not what I'm looking at here. The thing I'm looking at here says I need to view just x and y as functions of u and v. So how can I, if I have an extra variable here, if I have x, y, and z, but I want just x and y, how do I make that happen? Well, the answer is I project. Let's look at the shadow down in the xy plane. And I'm going to draw it just for, convenience of viewing this as a composition. I'm going to draw this projection as a separate function. And the idea being that what I have down here, the area of this projection, thinking of that as an image on its own. When you project down into the xy plane, I have in fact now just x and y, as functions of u and v. And thinking of x and y as functions of u and v, you know, this stretching factor here, x and y, functions of u and v, that partial, that little the determinant thing that we were looking at on the previous page, that determinant tells you exactly what the stretching factor is for this area, dx dy, how much is that stretched out of du dv. And of course, this area is the same as that area. So what we have then is this thing here that I very reasonably should call dx dy because it is an area in our xy plane. It's the area of the projection of our piece of surface down into this xy plane. Okay. So I am and really should call that dx dy. Okay. And having done that, let's see what comes out. So here it is, rewriting this partial, or this determinant, times du dv. I'm calling that dx dy. Likewise for the other coordinate Likewise for the other coordinate variables. By the way, there's some nice exercises in here. How would you make the analogous argument for dy dz and dz dx? It's a matter of thinking it through. Very analogous to what we just did. And having done so, here's what we end up with. This is where we were way back on the, a couple of pages back. ds is this product. We found ourselves wondering, what in the world am I going to do with this? Oh my gosh, I had this strong temptation to just kind of cancel these as if that's okay. Can I do that? Does that make sense? We've agreed that yes, I can call this dx dy. And the big punchline then is I now have a rewrite of ds. In the same sense that the dx vector had coordinates dx, dy, dz, the ds vector has coordinates, what you get by doing those little cancellations, dy dz, dz dx, dx dy. And that motivates rewriting flux integrals like this. F has components P, Q, and R, and you crank out that dot product. Flux integrals are sometimes written in coordinates like this. And again, let's go through the list. Why would anyone ever want to do this? What does this notation bias that somehow is in any way lacking here? And look, I'll be totally honest with you. I have a strong preference for this one in the Math 212 context. F.ds, it's compact. It's naturally meaningful. It's geometrically naturally meaningful. Right? This is a strong appeal for F.ds. It's easy to relate to F. Capital N du dv. Very nice. This notation over here is opaque from Math 212 point of view. Clunky, right? Big, bulky. So why would you ever do this? And pretty much the answer is, in the Math 212 context, I encourage you never to do this if you can possibly avoid it, right? But I show you, again, for two reasons. One is it's out there. And you will see this in your mathematical futures. You're going to see this notation. You need to know what to do with it. When you see this notation, you should realize that, okay, dy dz, dz dx, dx dy, that's their clunky way of saying ds vector. So these integrands, p, q, r, that's their clunky way of telling me the vector field of which they want to talk about a flux. Okay? So that's what I want you to do going forward. Be aware that the people who want to use this notation, they have good reasons. This is what a different kind of integral of a differential form looks like. This is a very powerful notation in ways that we can't use here in Math 212. So there's great reasons to want to do this. It's just not any reasons that we can capitalize on in this course. So when you see this, think this. That's kind of all you need to know about that. Okay. Great. We finished where I wanted to finish. Oh, I'm sorry I went 3 minutes over. I lost track of time there. Okay. See y'all later. Have a good Tuesday. See you tomorrow for the test. Okay. See my email about that.